So I know Feynman for a long time, like more than 15 years. So we had overlap at Georgia Tech. Probably we were in some courses in this field.
I don't think we take courses together, but I know one other faculty that I take lots of courses together.
And also had offices in the same.
Yeah.
So she got her PhD degree on Georgia Tech with Agata Lendrowski in 2011. And her research on fundamental theory and algorithm for convex maximization, structured non-convex maximization in operational machine learning and business analytics. So she got many awards. For example, the 2015 Informs Organization Society Prize for Young Researchers, and 2014 Informs JFP Best NS Career Awards. She is funded by NSF, ONR, AFOSR, and she is serving on Mathematical Material Society Council and on the editor board of Operation Research, Mathematical Programming, some Journal of Meditation, Math for Art, Informs Journal of Computing, Manifest and Software. That's all journals I can think about. Okay, so
You know who next year.
Not all the papers come to me.
okay, so without further ado, I think you should text.
Thanks. Thank you very much, George, for this nice introduction. It always feels like coming back home when I come back to Georgia Tech, and it has been a long time since I've been here. So thank you very much for hosting me here. Today, I'm going to talk about my joint work with my former PhD student, Alex Wang. He's now at Purdue Cranard, and it was really a pleasure to work with him. And he really has this very good taste in creating absolutely wonderful visuals. So every visual that you see in this presentation, I owe it to him. Okay, so today I'm going to talk about accelerated first-order methods for a special class of semi-definite programs. This, class is an important word here. It's not going to be applicable for all SDPs. Let's, start with that. And sorry. Okay, good. So here's what I'll do first. I will give you an overview of what's a QCQP. This is quadratically constrained quadratic programs. And from there, I will get into their famous relaxations, semi-definite programming relaxation. And then there's a reason. This is like a preliminary. I want to get you thinking SDPs in my way of thinking. Okay. And after that, we are going to see how certain structures in semi-definite programs that, govern their exactness properties. So that's the reason why I keep saying special class, okay? Where these SDPs have some exactness properties, how we can make use of those properties to develop fast algorithms to solve that special class of SDPs. Okay, that's going to be our final goal. Now, I'm going to do this in 4 parts. First, I'm going to give you these preliminaries on SDPs and QCQPs. And then I'm going to talk about a very, very specific quadratic program. This is the so-called generalized translation problem. Why I care about it? It's very simple. It is only a single constraint. So it cannot get any simpler than that, right? That's why I want to illustrate the ideas on that. And then I'm going to move on and talk about more general SDPs. In this special class, like if I'm looking for a low rank, specifically rank K solution, how we do this, how can we have that efficient algorithm? And finally, I will wrap up and conclude and point some future directions which are very broad. Okay, so let me start by talking about QCQPs. So QCQPs are defined as optimization problems where the objective function and the constraint functions are quadratics. Okay. So here, every function that you see is going to be a quadratic. I list it as less than or equal to or equality constraint QCQPs. Without loss of generality, I will first focus on less than or equal to type. You can transform one into another. And since we are talking about QCQPs, these functions that you see here, they're going to be quadratics. I captured the quadratic term with this AI matrix. in every QI function, and they can have linear terms or constant terms. So what does it look like as a picture? Well, my domain, I can have some linear constraints. I can try to be outside a Euclidean ball. That's a quadratic constraint. I can add more of those being outside, some non-convexity there. I can make it as complicated as I want, still keeping with quadratics. And then I can add a function. In this case, objective function to minimize is convex, but my domain is lots of non-convex quadratics, right? So in general, I'm not going to make any convexity assumption on any of these quadratics. Well, why do we care about QCQPs? They are highly expressive. You can imagine any hard problem that you want, and you can possibly express it as a quadratic program. In particular, take your favorite max cut, max cleat. They will be quadratic programs. If you look at applications in control, in statistics, sparse regression, you can write them all quadratic programs. Okay. In general, take any binary variable. It leads to a non-convex quadratic equality constraint. If you like to deal with them that way, you can deal with them. Or if you take any polynomial optimization problem, again, with a change of variable, you'll get to a quadratic program. Now, that said, this class of problems in general are NP-hard, right? So you cannot hope to optimize them efficiently unless you have specific structure. And but we still know they are a very broad class. Then what do you do in practice? Well, you look at a relaxation of the problem that's convex and efficiently solvable, and hopefully that relaxation has some nice approximation quality guarantees as well. Now that gets us to semi-definite programs. Okay, so I have this quadratic function over there, and I can rewrite it as this vector x1. I added that one coordinate here, so I can capture these linear and constant terms. I can rewrite it in this form. When I write it in this form, I can say, hey, let me label this data matrix over here, AI, BI, BI transpose, CI, let me label it as MI. Now, I have this product of a vector and the matrix and the vector itself again. So you can rewrite this as the inner product of your data matrix MI with the outer product of x1 vector with itself, right? Now, at this point, what I did, I'm just writing this in this specific form. I can do this for all the quadratics I have. I can end up with this exact QCQP. This is just a change of notation. I didn't really do anything fancy. I just rewrote it in this fashion. Well, so this is still NP-hard. Now, where does the relaxation come in? The relaxation come in when I say, hey, this particular matrix that was required to be rank 1 is no longer supposed to be rank 1, right? That is the relaxation we are doing. We are dropping that rank 1 requirement here, that x transpose becomes a matrix variable x. Now, this is the famous SDP relaxation. I hope everybody in this room has heard about SDPs and have seen SDPs in this fashion. And in general, we have this relation. SDP relaxation gives the lower bound on the QCQP. Okay. So, I want to introduce one other notion. One thing that's important here is once I do this SDP, I now have two groups of variables, one a vector x, another a matrix x. And in fact, I significantly increase the number of decision variables, right? The vector x, let's say, was in Rn. Now the SDP relaxation, it leaves this matrix x is in the space of symmetric n by n matrices, so it's n square variables that we have introduced. And that is a significant challenge when you try to solve SDPs. Now, I'm going to introduce a couple of objects because they will play a role in our analysis. So remember our picture for QCQP, that non-convex object. I don't want to deal with objective and the constraints separately. So I'm moving the objective to the domain by introducing this epigraph variable t. Now, my space has one more coordinate. I'm talking about the script D set. That's the epigraph of the QCQP. It's still a non-convex object. I just filled up this, above the epigraph of the objective function. Now, it's still a non-convex object, this script D, and you can say, hey, that's a non-convex object. What am I going to do with it? You can say, well, how about I get a convex relaxation for it, right? Very sensible. Okay, then you are like, okay, but you are dealing with this space that has nothing to do with SDP space. So you are going to talk about a different type of relaxation for it. Now, very trivial question. How can I obtain a relaxation for the script D set in this particular space, in the space of xt variables? I know the room is full of very smart people. I'm looking at the students. How do we do that? You know, this is your description of this set, script D. What do you do? Answer is really easy. No trick question there. Nobody? Really easy, come on. You have a bunch of inequality constraints. What do you do? Okay, let me make it a little easier. So instead of trying to derive convex relaxations, let's say I want to just derive relaxations for the script D. What do you do? Okay, that's not a very useful relaxation. It is true and it is convex, but not useful. Okay, what else can I do? That's your set, come on. What's the first thing you learn in linear programming? Yes.
We can have a lower bound function. That we have lower bound with another function. That one could be convex with a lower convex.
I dropped convexity already. I just want a relaxation. That's way more complicated than what I have in mind. What's the first thing that you learn in linear programming? You even teach this to undergrads. Go ahead. Lagrange, you aggregate them. Is that what you mean? You multiply the constraints with some non-negative numbers and you add them up, right? Yeah, you can do that. Everybody can do that. So let's say that this lambda vector lives in this dual space. Remember, I had m constraints here and the objective, the special one with the t variable. Suppose that I do that aggregation. So I obtain an aggregated inequality and it is always valid, right? It's always valid for that script D set. Now, okay, it's valid, but you know, this thing had some non-convex functions. Non-convexity is there, right? This aggregation that I get may happen to be non-convex as well. So before I get to there, I want to introduce this notation. I'm going to call this aggregated inequality Q gamma X, indicating that it's going to be a function of gamma, the aggregation weights that you use, and obviously it's the function of X. Okay. So, well, for particular values of gamma, I may end up with, if I'm lucky, with a convex inequality, like Q gamma X less than or equal to T. That's a valid aggregated inequality. But if I'm unlucky, which I may be lots of times, I may end up with a non-convex aggregated inequality that's still valid for that non-convex set. Okay? So far, so good. Everybody's happy, right? Now, if I come back and say, hey, I want to have a convex relaxation, what would you do? Well, you can just say, hey, you know, that's constraint you were able to derive. What if I just select the ones that are convex, right? And what are these things that we are driving? Well, these are indeed, this Q gamma X is a quadratic in X and a linear function in gamma, right? So I have this function Q gamma X, which is quadratic in X, and I really want that one to be convex in X, right? So what would I need? I would need the underlying matrix A gamma, if I define it like that, to be positive semi-definite. Okay, so now here's the cool thing. If you have never thought about SDPs in this way, SDP relaxation is exactly doing that. It's imposing all those aggregated quadratic inequalities that are convex. So if I were to draw the SDP relaxation in the XT space, it's like a projected SDP where I'm projecting out that X matrix in the SDP, then I would have this picture that relaxation will be exactly the intersection of all those convex quadratic aggregated inequalities that we derive. So if I make it more formal, I'm going to define a capital gamma set here. And that's going to be all the aggregation weights, non-negative aggregation weights, such that the resulting inequality is convex in X. And if I make it a little more explicit, that convexity is going to require me to have this matrix. This is that aggregation matrix to be positive semi-definite. Okay? So this is a very simple description of all those weights that will lead to convex aggregated quadratic inequalities. And my claim is the projected SDP set where you project out the matrix X variable is exactly the intersection of all those inequalities. So if I write it a little bit more explicitly, I obtain this XT set, the projected SDP set, as the supremum over gamma in capital gamma of these Q gamma X set function less than or equal to T. Okay. So I know people are very used to thinking about SDPs in the lifted space. I'm just telling you that, hey, there is an interpretation of SDP in the original space, and it is the main message of this talk is it is a useful interpretation to know. So, okay, so I can define now the optimum SDP value based on that interpretation. In this very nice way, we are minimizing in X the supremum over gamma of this function. Okay? Now, everything here, minimization in X is in the original space, but I have to deal with this function, right? And that could be a little challenge to deal with. So one thing you may say is like, I'm so used to thinking about SDPs as dropping the rank constraint. Now you are telling me, I just told you pictorially this is what's happening, but I gave you no proof of why this was happening. You can come back to your SDP, the favorite way you had your quadratic program expanded out in terms of the functions, write the same thing, quadratic program, drop the rank. Now this is your SDP relaxation. At this step, you need to realize you are taking the infimum over X and matrix X. And if you were to separate that infimum, which you can always do, and now take the dual of the matrix X, you exactly get that set that I introduced. Okay, so that's exactly doing your projection. Okay, I hope now you believe, indeed, this is going to be the optimum objective value of the SDP relaxation. Okay, so I think that was sort of end of my introduction. Now coming back, why do we care? Well, SDP relaxation is high quality and it's used a lot in practice. But a main challenge is, and it can be solved in polynomial time. On paper, SDPs is a nice class of polynomial time solvable problems. But the issue in practice is the dimension. They are usually too expensive to solve in modern applications because you have to do these interpoint algorithms or first order methods, and then you need to deal with this matrix X that requires lots of decision variables, right? In particular, classical interpoint methods will require, these are like path following methods and such, they will require lots of operations in every iteration. You'll do few, but still a lot of operations. And more critically, if you try to solve an SDP in practice, before you run into the cost of iteration business, you run into the storage business. The classical interpoint methods will need to store this matrix X and square variables, and then you need to store the dual slack matrix and square variables, right? So it's very expensive. You'll run out of space very quickly. Now, what we promise based on this approach is we say that we can solve a small class of SDP that have exactness properties much more efficiently, and not only efficiently in terms of number of operations, but efficiently in terms of the storage. So in particular, if I know the SDP has rank K optimality guarantee, now we can solve it with order Kn plus m storage. Like when K is small, the rank of that SDP is small. This is significant gain against this type of approach. And then we can solve it efficiently, meaning that our iterations will be very cheap. It will be only matrix vector products. Now, I will sometimes refer to this class as regular SDPs, and I need to introduce what that special class is. Okay, so the view that we will take to do that is this view of writing the SDP problem. Okay, and what's so special about this view? Instead of dealing with matrix variable, now I'm focusing on the original space, but I have to deal with this function. I have to deal with this function, which is a function of X. Okay? It is a supremum, but it's a function of X. And therefore, I will try to make those operations in the original space, not in the lifted SDP space. Now, and that will give me the efficiency in terms of the variables that we will be dealing with. And we will use the exactness property of the SDP. So these are going to be a very small special class of SDPs that will allow us to deal with this supremum, the max structure, efficiently and have very nice converging algorithms. Okay. So let me introduce what I mean by regularity or this exactness. So let's take the SDP problem written in this form, and let's create the dual problem. Now, I'm just changing the order of imp and sup. You cannot always do it. You have to have some assumptions, but in the case of SDPs, you can do it actually. If you assume, for example, dual strict feasibility, which by the way, I did assume even when I presented you this formulation. So, we will say, suppose now if we look at this form, we will say that the SDP is regular. If I look at an optimum dual solution, gamma star, and if I look at the minimum eigenvalue of the underlying aggregated matrix, okay, that minimum eigenvalue, this matrix here, A gamma of X, A gamma, I know by definition of the capital gamma set, this matrix has to be positive semi-definite all the time. Otherwise, it's not a convex quadratic, I wouldn't care about it. But what we will say is the instance is regular if it is indeed positive definite, if that minimum eigenvalue is positive. Okay, so we will focus on that specific class of SDPs. Now, what we will get by that assumption, well, you get a lot actually, that's a big assumption. The moment that you assume that dual optimum solution leads to a positive definite matrix, you are actually getting the optimizer exactness, meaning that the underlying QCQP, you can solve it exactly by solving the SDP relaxation. So that is a strong assumption. It's a big assumption. But, you know, I can just say, hey, there are some QCQPs that satisfy that property. So I'm going to see where I can go with that assumption. Okay. So let me tell you what, how this works when I actually work with a small or a simple class of QCQPs, and that's going to be our generalized trust region problem. So if you assume your QCQP has a single constraint, and suppose that your single constraint can be inequality or equality, but suppose your single constraint is a Euclidean ball. Okay. Then you end up with this class of problems called trust region subproblem. And that type of problems appear a lot in trust region algorithms and some other settings. But it's also well known that these type of problems have the exactness property. If you have taken convex optimization, maybe you learned about S-lemma, and that is exactly that setup. You have a single constraint, you have a single quadratic objective, one quadratic implying the other. S-lemma says SDP relaxation is exact for these problems. The GTRS is the more general version where you don't assume the constraint here is Euclidean ball. You assume it's a possibly non-convex quadratic. And in such a case, S-lemma also says SDP is exact, and problems of that kind also have their own applications. But the most critical thing is this family is a very simple family of QCQPs with exactness property for the SDP. And in most such instances, this mu star quantity that I defined, the dual optimizer, minimal eigenvalue of the dual optimizer, is positive. In fact, you can say that if you were given any instance and perturb it slightly with random data, then you'll end up with an instance that satisfies this property. Okay, so we were looking at the trust region problem GTRS, and we knew the convexal exactness and such. And it was like, okay, what's a good algorithm, an efficient algorithm to solve these problems? So given the view that we have, remember we are dealing with this view of SDP. Now, for this class of problems, I can say something even more. It's not just the optimum objective value of the SDP is the same as the GTRS instance objective value. You can also say that the convex hull of that non-convex script D that I have is given by the projected SDP. Okay, so this is a little stronger property. And in fact, for this class of problems, since it's so simple, I can try to see what's that gamma set that we use to define the SDP. And remember, I have a single constraint, so that gamma is going to be on the real line, right? So what is that doing? Gamma is now just a non-negative number, and we want that quadratic to be convex in gamma. And what we are doing is when gamma is 0, we had this non-convex quadratic given by our constraint. And then slightly, we are adding more and more of the objective function to it. Right? Sorry, we have the objective function. We are adding more and more of the constraint to it. So we are generating a bunch of quadratics, right? And since I assume strict feasibility, strict dual feasibility, somewhere along the line, I must have a convex quadratic. And before I transition to that convex quadratic, there will be a first point where my quadratic will start being convex. And possibly there will be a last point where my quadratic stops being convex. Because as I increase gamma, take it off to infinity, it's going to look more and more like my non-convex constraint, possibly, right? So this means that this capital gamma set is just going to be an interval, gamma minus to gamma plus. Now I know. Okay, so for that very simple class of problems, then this says, hey, your SDP relaxation is exactly given by this formulation. So I'm just putting what that capital gamma set is. And in fact, you can say, you don't need all of those gammas in between. You can just focus on the endpoints. Okay, so what is this now? Well, it's a minimization in X, maximum of 2 convex quadratics. That we can do. Right? This suggests an approach, and indeed, this is what we did first many years ago in 2020, which the paper got published in 2022 in math programming. But we said, okay, let's get those convex quadratics, and let's look at their maximum. So that's going to give us this set. This is going to be giving the exact convex hull in that space. And algorithmically, what do you do then? Well, you can say, I'm going to compute these endpoints, gamma minus, gamma plus, to some accuracy, to high accuracy, maybe. I'm going to build my convex reformulation. I'm going to solve convex reformulation for accelerated gradient descent for smooth minimax problems. Nestor has a nice chapter on this, actually. It's going to be, I will come back to that chapter a lot right now in this talk. Well, what do you get? You get this type of convergence rate. This N is the sparsity of your data, like number of non-zero entries in your matrices A. You have roughly order 1 over square root of epsilon convergence, epsilon being the additive error in the objective value. Okay? So you can say, hey, great, all done. Now I can solve these problems fast. 1 over square root of epsilon is not bad. We are done. Well, you can ask, is this the best rate? That is the rate that I told you. Maybe you'll say, yes, possibly, because I can formulate the minimum eigenvalue problem as a quadratic, exactly like a truss region problem. And this is the complexity of finding the minimum eigenvalue. You can say, hey, this is like a smooth convex quadratic minimization. And again, well-known lower bounds on that. All order of 1 over square root of epsilon. But numerically, when we tried to solve these, it turned out we were getting faster rates. And then we wondered why, what happens. So we started investigating, and we realized these problems where you all get 1 over square root of epsilon are the hardest instances in the GTRS family. In fact, for these problems, like for example, minimum eigenvalue problem, that problem is not regular. That mu star quantity I defined is always going to be 0. If you look at this smooth convex quadratic minimization, again, there are some functions where you don't have that regularity. So now the question comes, if we know mu star is positive, which happens a lot in practice, then can we do something better? And indeed, we can. So this was our next observation. And let's say mu star is positive. So what does that mean in terms of our picture? Non-convex set. Now when mu star is positive, it means that at the dual optimizer, there is a strongly convex quadratic matching with the objective value of the SDP at the dual optimizer. So at gamma star, you have a strongly convex function that has exactly the same objective value. Okay, so well, in fact, if you look at the original reformulation I mentioned, okay, so many steps here. The design of these gamma minus and gamma plus, by their design, they are such that they are not ever going to be strongly convex unless both of your A1 and A objective and A1 are positive definite, which is not a very interesting case. Okay, so if you do this reformulation, you never get that strong convexity. But if you know this mu star is positive, then you know that at the optimum, there's a nice strongly convex function, and you want to get there. Like you want to use strong convexity is very useful when you try to get, better convergence rates. So in order to do that, you can say, well, what if I find a smaller interval, not the entire gamma set, a smaller interval that contains that dual optimizer? Then at that smaller interval, you'll also have strongly convex functions. That's going to be the goal. And then now you can do faster algorithms. So in such a case, you can say, I'm going to optimize on that smaller region close to gamma star, and I'm going to be able to do strongly convex minimization algorithms to accelerate. Now, what do we do in such a case? Well, if we try to find these endpoints to high accuracy, this is going to be expensive again, because we are essentially doing something close to an eigenvalue computation, which again, we get back to 1 over square root of epsilon. Instead of high accuracy, we want to estimate them to low accuracy. Okay, and we can show that you can estimate it to low accuracy, and then you can take advantage of strong convexity. And when you do that, you obtain this convergence rate. So this rate explicitly depends on how strong convexity parameter of your optimum dual optimizer, right? And that is sort of expected. But one critical thing is this is order log of 1 over epsilon, and that sort of match with the behavior that we have seen in the numerical instances. Okay.
You need to know mu star.
Sorry? No, we don't need to know mu star. And the algorithm will try to find the accuracy, this low accuracy based on the estimate to mu star. Okay. So the algorithm is actually just doing. No, it doesn't. So the algorithm, the algorithm will try to balance finding these approximate gamma minus tilde gamma plus points. And then it will try to do that accuracy to a level that's going to be okay with the goal.
And a couple of things. One thing is basically these are number of iterations, right?
Yes, and the iterations are cheap, just matrix vector. We never do eigenvalue computations.
Because at least even to get your estimate, like basically to get this capital gamma, right? Like
we never compute the capital gamma though.
Yeah, but in this case you compute 2 points, yeah, some estimate of it. So, but then how would you do that? Like, when you say low accuracy, what does it even mean? Like, you want to say you can do it faster than eigenvalue computation?
Yeah.
And what would because intuitively, like you also argued about the space is quadratic, right? When you're in the SDP. But in this sense, like checking feasibility is checking eigenvalue of an n by n matrix, right? Like checking feasibility of a particular gamma.
Right? So that's a good question. But what we do in this algorithm, and I will tell it in the more general terms, is we are indeed not guaranteeing feasibility right away from the get-go. So the algorithm, I have it sort of written over here, the algorithm is solving this problem. We will first get to a point that's like epsilon approximate in terms of this entire objective. And that means my point, the first point I get to, is not necessarily feasible. Okay? And then you can do a very cheap rounding, because the rounding will be very simple in this case because you only have one constraint. Okay? And then you can guarantee feasibility. So I'm not talking about the very general SDPs yet, right? This is a very specific case.
Yeah, sorry to be one more question on this, but basically because you have the single constraint, you know this is the same as SDP. Right? Because you're not losing anything in this relaxation. Sorry, like in the sense SDP is exact as well, right? Like
SDP is exact, yes.
Yeah, so but why did you need to, like you said, you still assume
mu star is positive.
Because even if it is 0, we know.
Yes, we know things are still fine, but we cannot get this rate. If mu star is 0, then we are stuck. We don't have strong convexity of the objective function. We cannot get this rate, but we will be able to get the other rate that I showed you, like 1 over, so all these rates 1 over square root of epsilon. So you'll hit those barriers because you cannot guarantee strong convexity of these type of problems. Okay.
Since you don't need from mu star, so is this a unified algorithm that you can apply to both statements? Whether mu, no matter whether mu is positive or negative?
You can apply the algorithm, but the convergence rate you get to see will depend on whether mu star is.
This algorithm is specialized. It's different from the previous one.
Oh, I'm going to come to that when I talk about numerical results. Yes, this algorithm is very different than the one that we originally presented that was getting us 1 over square root of epsilon, because this 1 over square root of epsilon algorithm was really relying on high accuracy estimation of that gamma interval, those endpoints, finding them well, which relies on eigenvalue computations, as Mohit was asking, and therefore it was expensive. Right. Okay.
You did say on the structure of your problem that mu star is greater than 0. What is it really capturing?
It's capturing that the strong convexity underlying the dual problem. That is exactly what it is capturing. So let me come back to that mu star definition. Oh, it's a lot of slides. Okay, here, what's mu star? Mu star is defined in exactly this way. And I know I wish I had written this Q gamma X written explicitly. But Q gamma X is X transpose this matrix times X and so forth, right? So what this is saying is when mu star is positive, it's saying that at the dual optimizer gamma star, I have a strongly convex function, okay? So I know for any SDP, like any G-trace instance, I know this mu star is non-negative, but that means some of those instances may not have that strong convexity property. Yes, please.
Examples, maybe tell us a little bit more when this applies.
Like beyond strong convexity.
So I mean, like, for example, you talk about tractable problems. Those don't all apply. So is there like a subset of problems where we always know that it was bigger than 0, or is how do we detect when you know?
For example, if you look at the minimum eigenvalue problem, which is a very well-defined problem, then this mu star is always 0. Okay, so you never have that strong convexity property. If you look at something more like a random trust region problem or a random GTRS instance, almost always will have mu star positive. Okay, so now what we discovered that looking at this view and thinking about the dual optimizer and whether the dual optimizer can have strong convexity or not makes a difference in terms of the convergence rate of the algorithms. Okay, so let me show you a couple of slides with numerical results. We tested this on a number of instances. In fact, we submitted the original paper where we were saying, hey, reformulate this problem using the gamma set exactly. We submitted. And one of the referees were like, hey, why don't you have some numerical results? We said numerical results in another paper. So we really started doing numerics first. And then we noticed this behavior and we were like, hey, we need to analyze what's happening. And we come up with this, hey, strong duality of the dual is important here. So let me decode this for you. The purple one is the new algorithm, which relies on strong convexity, that mu star. Okay, it never builds that gamma reformulation exactly. The blue one is the old algorithm that actually does the gamma relaxation exactly. Okay, that is like 1 over square root of epsilon convergence. Even then, you know, this was very fast convergence. The orange one is Adachi Nakasukasa. That's an eigenvalue-based solver. It just increases the dimension even further. If you were dealing with X in Rn, now they are doing generalized eigenvalue computation of a 2n plus 1 times 2n plus 1 matrix. So, you know, eigenvalue computation. And then the green one, JL, that's Zhang and Li. It's another type of solver. It's a linear time in terms of the sparsity of the data, but it's again order 1 over square root of epsilon type solver. And we have Bantal-Hertog that simply says, hey, this is GTRS, that's okay. I can reformulate it in a lifted space as a second order comp program and hand it over to solvers, lots of great solvers for second order comp programs. Okay, so that's the orange one. Now, this is a very small instance when n is 1,000. And we generated, in this case, we can control the mu star. And here we generated a relatively good strong convexity at the dual optimizer. And the problem is relatively sparse. N is the number of non-zero entries. So even then, we see that our approach with low accuracy estimation was doing well. But we tested a couple of things. Now we look at, for example, what happens if you really make that strong convexity parameter small, 10 to the minus 6, right? Even then, it looks like we are doing okay. And then what happens if you really start increasing the sparsity? Now the problem gets dense. Okay, and dense problems are difficult for solvers, second order con solvers and such. And when you start increasing the density, you start seeing like different type of behavior. So this is still n equals 1,000. If you increase the dimension of x, now things start looking very different. All those solvers, even a second order con solver that Bantal-Hertog uses, becomes quite expensive. So you don't get to see that in these graphs. And you get to see these eigenvalue-based solvers are, again, not doing very well. Okay, and if you increase it even further, like 100,000 is the dimension, again, the picture looks like it. So the conclusion is this idea of trying to, like, you almost always have this strong convexity and exploiting that in the algorithm seems to work well. Okay, so, you can say, oh, that's cool. If you have a GTRS, you can do that. You can say, how often will I have a GTRS, just a single quadratic constraint? Now, from there, we were thinking, okay, can we expand this to solve larger classes of SDPs? Okay, so in particular, can we handle SDP relaxations of QCQPs with multiple constraints? That's one thing you are interested in. With QCQPs, it's really specific because you are looking for this rank 1 solution, right? Ideally. You can also say, hey, there are SDP relaxations where I don't just want rank 1 solution, I want maybe a rank K solution. Can I expand this idea to handle that as well? Now, the way that I define mu star should inspire you to say, yes, the answer is yes, please. Okay, because I didn't define it just for GTRS. I actually defined it for more general settings with multiple constraints. So let me tell you the general setup here. Now, I'm starting with the SDP written in this form. I switched to equalities, but I don't think that's a big deal. And I'm looking at this dual problem. Okay. So I'm going to call this dual slack matrix M gamma that you can obtain. You can think about the gamma in the very same way. Okay. We are going to focus on this special class of SDPs, and we will call them K-exact SDPs. So I'll have a bunch of assumptions, and we will discuss these assumptions. So first, for this class, I'm going to assume strong duality holds, and we both can attain primal and dual optimum solutions. Okay. So we can debate, but I'm going to just go ahead and make this assumption. The second one is even stronger. I will assume strict complementarity holds. What's strict complementarity in this case? It means that I have a primal solution Y star and the dual solution gamma star, such that the primal solution is rank K. And the dual solution, the slack matrix at the dual optimum, is rank N minus K. So they're really making that complementarity. Okay. So maybe that's okay. In fact, there are older papers that studied strict complementarity. And if you assume primal and dual attainment, then you are very, it holds generically that your problem will satisfy strict complementarity as well. So it's not such a big deal. The big deal will be these numbers, this K that we are trying to assume. Okay. The final assumption may look a little different. In the final assumption, I'm saying that we know of a subspace W of dimension N minus K. It's the same K. And what else we know about it? We know that my primal solution restricted to the orthogonal complement of W is known a priori, and it is positive definite. Okay. I know this is a lot. Like, what is that thing that I'm talking about, this last assumption? You probably have never seen that before. Okay, so let me motivate what that last assumption comes from. So in this talk, I'm going to assume that W subspace I'm interested in is Rn minus k. This is just going to simplify my notation. Otherwise, you can do a reparameterization of your problem. And then if W is Rn minus k, I can take W complement to be Rk. And I will assume this Y star primal optimum restricted to that subspace, remember, is known and a priori is our assumption. I'm going to assume that positive definite matrix is just identity. Again, another reparameterization. Okay, so that is this is just for notational simplicity. It's not an assumption actually. Now let's talk about that W subspace. Where does it come from? How will I magically know such a subspace? Okay, so let's look at the SDP relaxation of the QCQP. Okay, remember we had this form, and remember we had this one on that corner. So in such a case, you will take your W to be Rn minus 1, and you particularly know the restriction of the optimal primal solution to the complement of W on that is exactly 1, which is positive definite. So that is not such a bad assumption after all. Like for the way that we derive relaxations, we actually know that. Okay. Now, what else can I say? Is there another application? Well, you can look at quadratic matrix programs. These are special optimization problems that looks like quadratic programs, except instead of the decision variable x being in Rn, now you have a matrix variable x, capital X, in Rn times k. Okay, and instead of having the usual quadratic functions, now you have quadratic matrix functions. Okay, it's just exact analogy, and these type of problems have been studied in the literature before. In fact, some exactness guarantees for them are known too. Now, if you look at a general quadratic matrix program, you just have this type of quadratic matrix objective and constraints. And, it has its own applications. In general, if you have a highly symmetric QCQP, you can write it as a QMP as well. Now, if you look at a quadratic matrix program and it's SDP relaxation, again, you do this and you end up with this corner. Okay, this corner ends up being positive definite. It's exactly this identity matrix. So this type of assumption where you know a subspace W and you know your optimum solution restricted to that complement of W and so on, that is, motivated by the practical way that SDP relaxations are derived. In this case, again, W is Rn minus k, and that is exactly identity. Now, let me come back to our assumptions. So it sounds a lot like, okay, all these problems, QMPs, QCQPs, indeed, this last assumption is satisfied, right? I told you, hey, it's satisfied, hey, it's satisfied. Then why do I keep saying it's a very special class of SDPs that we can solve? What's the, special thing going on? The special thing that's going on is that, remember that K, the dimension of that subspace being M minus K. In the case of QCQPs, that K ends up being 1. And here, with the strict complementarity property I'm talking about, I'm saying that, hey, the optimum primal solution is rank 1, essentially. Right? So together, these things all together is really assuming exactness of the SDP relaxation. And in particular, for example, if you take K exact SDPs originating from QMP, then they admit exact SDP relaxation. So I'm really talking about SDP relaxations that are exact. Like, it's like a generalization of trust region problem, but it still assumes that very nice exactness property. Okay, so what can I do? Well, we want to do the same thing. We want to build a strongly convex reformulation of those exact SDPs in the original space. Now, we will do the following. We will say, hey, this optimum primal solution now needs to look like this. This is our assumption on that subspace W. right? And I'm saying that, hey, it must have this type of structure because of strict complementarity, right? Okay. Now I'm going to reparameterize my optimization problem with Y matrices that look exactly like that. So I'll put that identity over there, and I will specifically look for a low rank matrix right here. Okay, so our constraints or objective will become optimization problems of this form. Now I can reparameterize these MI data matrices. I can partition them based on the partition of my primal solution. Okay, and I have a bunch of data associated with it. I can rewrite all of this as a function at variable x. Okay, now what does that function look like if I expand? Well, it looks like a quadratic function in the matrix variable x. So I start from that SDP with linear matrix equations or inequalities, and knowing that it's going to be a low rank, and plus knowing that there will be an identity over there because of the subspace assumption. Now I'm coming back and reformulating that as quadratic functions. So I reformulated my nice SDP as a quadratic matrix program. Okay. Now at this point you should be like, okay, but you know, QMP was this hard problem, like a generalization of QCQP, MP hard. Now you get your SDP back to QMP, what did you gain? Like, why are you doing that? Well, in fact, I will even switch over and this Lagrangian view of that one. And all these steps should look similar to like the GTRS thing that we did. So I'm going to go ahead and define this notation of this function Q gamma x as well. Okay? And that is going to be a quadratic matrix function. Now, at this point, I don't, Montero is not here, but if he was here, or anyone like Diego, you should ask that. That looks a lot like Buer-Montero method, right? You are factoring everything out. It looks like you are using the low rank assumption, so what's different? Right? In fact, if I come back and look at the Buer-Montero method, I have this SDP, and I use the low rank assumption. If I know, for example, SDP solution must be a rank K solution, I would do this factorization with this x tilde. I will rewrite it, and I end up with this quadratic matrix program as well, right? So what's different? Well, the thing that's different is that in our formulation, we assumed we know this W, right? And because of that, we were able to actually identify a part of our solution, this x tilde that's used in Buer-Montero method. We were able to say that a part of that solution is just identity, K by K identity. Okay. And why do we care? Well, we care because that way, that particular way that we fix that corner is breaking the symmetry. So if you apply Buer-Montero method to an SDP, even with exactness, you are not guaranteed that you can obtain a strongly convex formulation. You may end up with, you know, multiple optimizers. And by breaking that symmetry, we are now able to exploit this SDP exactness and strong convexity together. Okay, so that's one little difference, but it makes a difference in the implementation, in the design of algorithms. Okay, so let me wrap up this idea. Now, with strong duality and strict complementarity, what we can say is that just like the GTRS, we can say that if I look at the optimum solution to this problem, this is the QMP that we formulated, I can say that this is going to be exact optimum solution to the underlying SDP. So it's going to match with the optimum dual solution gamma star. And if I were to solve for that optimum dual solution gamma star and find the corresponding matrix coming from there, then it's going to be X star, and I'm able to do this reformulation. Now, strict complementarity also tells us that this matrix A gamma star is going to be positive definite. This is exactly what we did with GTRS. We were able to get that positive definiteness. Okay, and this means the underlying function Q gamma star X is going to be strongly convex. Okay, so the whole thought process is very similar, but there are several challenges. Like in the GTRS case, the capital gamma set was so simple, it was an interval. Now I'm really talking about a capital gamma set, it's an SDP. Given me as an SDP, it's much more complicated. How are we going to do this? Right? So in fact, if someone magically tells me that here gamma star is your dual optimizer, now solving the problem is very simple. I just optimize for that gamma star, I find the optimum X. But no one is going to tell me that gamma star. Okay? So what we can say is if you are close enough, if you are in a nice neighborhood of gamma star, all those nice properties will carry on. So to that, we define this concept of certificate of strict complementarity, which we say you want to find this U, script U. It's a neighborhood of your dual optimizer. Just like what we did with GTRS, you are trying to find that neighborhood that contains your dual optimizer, and you are positive definite for that neighborhood. Okay? So you are in the nice region where you have strong convexity for every point in that script U, and you are saying that, hey, my optimizer is there as well. Okay, so you want to have that nice neighborhood certificate of strict complementarity. Okay, so far so good, but how do we even compute that neighborhood? How are we going to do all of this? So if you do have that neighborhood, then your optimum SDP solution is going to be given by this problem. Instead of optimizing over gamma, now we can optimize over that neighborhood script U. But how are you going to find that script U? That's not trivial, right? Besides, you are eventually solving an optimization problem. You rather have that script U to be nice, like maybe nice projections, something of that form. So we will call this as a quadratic minimax matrix problem. That's QMMP. And we have these questions left. How can we construct that script U? And once we are given that script U, how are we going to solve the resulting problem? Okay. So I'm going to start with the easier question. The easier question is, what do we do once we have that formulation? Someone gives us script U. And that is sort of easy, but not so easy. The nice thing about this problem is now we know it's strongly convex. It's a strongly convex minimax. And it's this very nice chapter. Say it's a vector, it can be a matrix. So in fact, we can use accelerated gradient descent to solve problems of this type, which is good, it's nice. The issue is, if you try to apply that algorithm, it does something called a prox mapping step. I didn't write it out, but it builds a nice approximation function to your original objective around a given point, and then it's a quadratic function that you need to optimize. And that prox mapping step in that book is assumed to be exact. Like most of those applications had an exact formula for that prox map, or you can, efficiently solve it with some algorithm. So we had to develop a technique that handles approximate prox map computations, because in our case, that prox map doesn't have an explicit solution. And we have to then create a variant of this accelerated gradient descent that can handle the errors. The errors don't accumulate. Like over iterations, we do those solves. Like we solve this prox map as an optimization problem itself. And over iterations, we increase the accuracy to which that we solve that optimization problem and show that overall those errors don't accumulate. And we call that algorithm cautious AGD because its step sizes are smaller than the typical one. Now, that algorithm guarantees us this. We are going to be able to optimize this problem in additive error epsilon in order of log 1 over square root of epsilon. I'm sorry, order of 1 over square root of epsilon, log 1 over epsilon iterations. And all those iterations will be just matrix vector products. Okay. Now, this is still sidetracking the bigger issue of finding that script U set, certificate of strict feasibility. And well, that could be a big challenge. But here's the thing, we know that if we find the right U, we have this convergence rate, right? So we can say, well, what if, and we know that strict complementarity, that certificate must satisfy these conditions. It must contain our dual optimizer, and it must have every point in that set must be positive, leading to positive definite matrix. So what does that mean? It means that I can run an algorithm, maybe a small algorithm in the dual space. The dual space is in Rm. So if you have few constraints, that is still fast. I can have an algorithm that will slowly converge to that gamma star. Okay. Now, for that, I can say, I can check if someone tells me a point, gamma 2, let's say, I can check whether the underlying matrix is positive definite or not, right? So for all those positive definite points, now I have to think about, can I have a ball around them that hopefully contains gamma star, right? You can say, I'm going to create a ball and check if it contains gamma star. How am I going to check, though? How are we going to do that check? Well, it's not trivial to do that check, but we can track. Like we know that if we are close enough to gamma star, if that U neighborhood indeed contained gamma star, we know that our algorithm, cautious AGT, will converge fast, right? We can track how fast that algorithm is converging. And if we see that it's stalling, then that's our clue to go back, find another gamma T and iterate. And this is the overall framework. So you actually generate the sequence converging, dual sequence converging to gamma star. And you check, you keep checking how fast for that particular ball that you created around the gamma T point, you are converging in cautious AGD. And if it's not rapid enough, you find a new dual solution. So the overall framework will give you a guarantee of this form. So an additive error in the objective function, some possible constraint violation. Okay. And the overall number of iterations we will do is order 1 over epsilon, log 1 over epsilon. And the iteration complexity is again just matrix vector products. So it's really fast. And more importantly, we never store the big the big Y matrix. We only store the rank K, like X matrix, and that gives us the space advantage. Now, I'm out of time, so let me quickly talk about the numerical results. We tested this on specific instances where we can control exactness, and these are randomly generated distance minimization, quadratic matrix programs, quadratic matrix equations subject to this particular objective. And we generated instances where K, this rank of the optimum solution, is small, 10, and number of constraints is small as well. But the dimension X is big. And we compared against some algorithms that are storage optimal or like low storage algorithms and some standard software. CERT SDP is our approach. CS SDP is complementary slackness SDP algorithm by Li Junding and Madeline Udall and so on. It actually does something similar. It finds that sequence for the dual optimizer, but at every iteration, it restricts, it looks at the matrix of the dual problem and then looks at the columns. Based on that, it solves a specific low dimensional SDP. And then there is the prox SDP. It's like a proximal point algorithm. There's SCS splitting cone solver. These are more generic solvers. And I want to give you the clue about what I was talking about convergence. So here on this plot, we are looking at the primal square distance and the dual optimality error. So you can look at this top line where that's telling you what's the dual error. Like in terms of the dual error, we are doing pretty bad. Like the convergence to dual optimal is slow. But when for every iterate of the dual solution, remember that occasionally we are solving the QMP with the corresponding U. And for those, we are tracking what's the convergence in the primal. And we see, for example, here, it's stalling. That means that's our clue to switch over and find a new dual iterate. And then you keep going until you don't see that stalling behavior. And then you really get these all very nice high accuracy solutions. Now, if you compare against the competitors for smaller instances like n is 10, n is 1,000, you get to see that our approach is getting very high accuracy solutions, and the corresponding solution times are very small. This prox SDP is like a generic solver, and it works really well for small dimensional problems. The CSSDP in our instances, this Udalin et al. Solver, unfortunately, is not really giving us high accuracy solutions. It's sort of stuck around this dual optimality gap. And SCS is a generic solver. So if we increase the dimension of instances, remember this is to make the SDPs more approachable. So you really care about larger scale instances. CSSDP drops from the picture because it doesn't do anything special for low rank. And again, we are able to get high accuracy solutions relatively fast. Again, the same behavior with CSSDP, and the behavior with prox SDP is starting to go bad. And if you increase it even further, these are very large scale instances. N is 100,000. They are really big, very difficult to solve for any problem, any software. And we see our errors are, not as good as before, but still decent. And the solution time, again, is high, but these are very large scale. So I'm going to give you the memory footprint information too. The certified SDP, our approach, and CSSDP are very low in terms of the memory that they require. By design, they are working with low rank matrices. On the other hand, these more generic solvers, prox, SDP, CSC, they drop out of the picture quick because of the memory footprint that they bring. So just to wrap up, I hope by now you are convinced that QCQPs and QMPs are really interesting. They are highly expressible, but they're also very difficult. And SDP relaxation is a very common approach to solve those. And if you are trying to solve rank K exact SDPs, if you really are lucky to have the exactness, then you can exploit strong convexity to get some very nice efficient algorithms. Well, this brings up the question of how often will we get those very nice class of problems? So in general, if you have different classes of problems and you have this nice exactness property, can you also talk about faster algorithms to solve those type of problems? Okay, not just this nice exactness, but also faster algorithms. And more generally, well, what happens if we take this algorithm and this framework and apply it to a problem where your solution is not guaranteed to be low rank, but it's approximately low rank? Would it still survive? Okay. So these are very broad. I think making progress in these directions will really help us solve problems in general, but I can imagine making progress is not going to be easy. So thank you again, and I apologize for the overtime. I got more questions that I typically get. And if you are more interested in results, the first paper is about the trust region problem, just to give you the high level of the idea where it came from. And the second paper is from this summer. It's more on SDPs. Yep.
Are there any questions?
Yes, please.
You assume that you have the qualified
Yes.
The smallest eigenvalue is true because the nut matrix is positive definite. And then your SDP constraint is that.
In the dual, you mean? That matrix is in the dual. The matrix that you are talking about is in the dual.
Yeah, but it's still what? If it's, does it mean that it's
no. It's not the matrix defining the dual constraint. It's an aggregated matrix.
Isn't that what you're querying?
No.
That's one way to ensure that it's.
So it ensures it doesn't say, you know, you can drop the SDP relaxation altogether. It says that the optimizer of your dual optimizer of your SDP is in the interior of that gamma region. Does it make sense? Because gamma was the region where that dual slack matrix is positive semi-definite, and now you are saying that my optimizer is in the interior because it's positive definite at the dual optimizer.
Yes,
It's in the dual. No, you cannot really drop those constraints. Like, it's not a particular constraint you are dropping. It's simply saying that instead of trying to deal with the all possible things that's defining the boundary of that gamma region, you can simply focus, because you know it's strictly in the interior of your gamma region. It's saying that you can actually simply focus around that neighborhood.
that means that it has a special one on your but it's not high with respect to the other. That's what you mean. It's not high with respect to the object. It's fine. You cannot remove the constraints, but they are exactly not binding with respect to the object.
So it's saying that the gamma region that's defining your dual problem, you don't need that region exactly, because your dual optimizer is in the interior. Therefore, if you have a nice neighborhood in the interior contained in that gamma and contains your optimum solution, then you can just focus on that. Yes, Diego?
When you're finding the issue, you said that doing the check if it works is that you just run the method to see if the convergence rapidly enough. Could it happen that the rate is correct, but it converges to the
No. So in order to find u, what we first do is, first of all, you have these gamma i's. Now, around gamma i's, you can define some Euclidean ball, and you can define it so that you know, if the A gamma is already not positive definite, you just throw it away, you have to continue. And if it's positive definite, now you can define a radius around that point so that that neighborhood is contained in the capital gamma set. Now that's not enough, because you really want to contain gamma star. And if you are not close enough, then you can show that your convergence is going to stall.
It's not gonna restore.
No, it's just going to stall. It's going to be like you won't be making progress in terms of the distance, the squared primal distance to the solution.
So maybe we should put the questions offline.
Oh, sure.
Yeah.
Thank you.
Very nice. I think very clear.